Let's use another example to find out a little bit more about how to find that steady state vector, aside from just hitting enter over and over and over again on your calculator. We are mathematicians. We will be more clever about it than that. So I'm just making up these particular numbers and this application. I mean, whether it is sunny or cloudy or rainy the next day. Actually, maybe that is life and death for some people, but there are definitely more interesting applications, I think. But I just made up some numbers. You could probably look at some weather records and get the actual percentages around here. But I just said, suppose that if today it's sunny, there's a 20% chance it'll be sunny tomorrow, because, hey, this is Washington. A 40% chance it'll be cloudy, and a 40% chance it'll be rainy. And I made up some numbers for cloudy and for rainy as well. So let's set up the stochastic matrix for this. Keep in mind, a stochastic matrix has a probability vector for each of its columns. And if it helps, sometimes I write just a little from up here and a to over here to say if you're going from a sunny day to another sunny day, what's going on. And you can say, so that's sunny, cloudy, rainy, sunny, cloudy, rainy. So if that helps, do it, but also just make sure that each column adds up to 1. So the first column is about being sunny. So the next, if it's sunny now, probability will be sunny again, 20%. Probability will be cloudy, 40, and rainy, 40. So if it's currently cloudy, 10% of those days will become sunny, 70% of them will be cloudy the next day, and another 20% will be rainy, and 0.05, 0.5, and 0.45. Okay, so there's our stochastic matrix. It tells us how things transition from one day to the next. And then we need to start things off. So looking out the window right now, it's sunny. So today there's a 100% chance it's a sunny day and 0% chance that it's cloudy or rainy. Today is sunny. But let's go ahead and see what the probabilities are for tomorrow. And really what I'm interested in are the probabilities for like a week out. I mean, my matrix already tells me if today's sunny what the probabilities are for tomorrow. But what's the probability it's going to be sunny a week from today? So let's just start with basics. There's our stochastic matrix. So we want to multiply that by the current state, which is a sunny day. So we'll go ahead and multiply that out. And that just tells us that tomorrow there's a 20% chance it'll be sunny, a 40% chance it'll be rainy, 40% chance it'll be cloudy. We knew that already. It's basically just replicating the first column. But I'm now interested to say, how about day after tomorrow? Say, well, tomorrow there's a 20% chance of this, 40% chance of 40% chance of that. So those chances, if we run them through and say, how about 2 days from now? Say, well, 2 days from now, there's a 10% chance it'll be sunny, and a 56% chance it'll be cloudy, 34% chance it'll be rainy. So let's just do a few more days. I think I said, what about a week from now? So that's tomorrow. So we've done 2 days so far. So let's get up to day 7. So there's tomorrow, next day, third day, fourth day, fifth day. I just know one of you is going to send me an email saying, you can do that with this so much easier this way. Actually, I hope that somebody does. Please send me an easier way to do this on Microsoft Mathematics. But anyway, let's see. I think we're on like day 6 now. So let's do one more day. Oops. Let's get rid of one of these. Come on. So if I didn't lose track, I think maybe that's day 7. So it says, if today's a sunny day, there's about a 9% chance that we'll have a sunny day a week from now, 61% chance that it'll be cloudy, and 29% chance that it'll be rainy. That's very close to what the previous day was. So it kind of looks like we're already getting into our steady state vector. Let me run it through 1 or 2 more times. So that times that. Yeah, the results that are coming out now are very similar to what's going in. So I think we're going to kind of get this same thing over and over and over again from here on out. We're basically at the steady state vector, which just says if you start with a sunny day, long term you're going to end up with about 9.5% of your days sunny, 61% of them cloudy, 29% of them rainy. Does it make any difference if we start off with a rainy day today? So let's go all the way back to the beginning and say, suppose that we started with a rainy day, 0, 0, 1. Let's multiply that out, and I have to go all the way back here and here for the next day. Back to here, here for the next day, here, 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 yep, for the next day. We're actually, even though we started with a rainy day, we are already getting pretty close to our steady state from before. About 9.5, 61 and 29. About 9.5, 61, 29. Turns out the steady state vector does not depend on the starting conditions. You'll always end up balancing out at the same behavior long term. So we need to find this steady state vector in a more efficient way. Before we dive into that, though, I just wanted to point out that this sunny, cloudy, rainy idea, like I said, is just a kind of made-up application. But to get a couple real-life applications, first of all, Markov, the man himself, he was a Russian mathematician, and he was very interested in poetry, so he applied this. What other Russian poet is there? That's right, Pushkin. He applied this to Pushkin's poetry, and he looked at whether a vowel was followed by another vowel or by a constant. And he did a whole bunch of computations with that, just basically turned it into a linguistic analysis of how likely certain words were to pop up. It was really interesting, although I didn't understand half of it. But I just love some of his work. Like, this is his handwritten count of some of Pushkin's poetry. That old school mathematics is just almost visual poetry in itself. But more recently, well, actually, this is a Chuck Stevens application. He's another instructor in the math department at Skagit. And he really likes applications of Markov chains to games of chance. So this is a pinball machine and pachinko machines and things like that. So this one is saying, suppose the ball is somewhere in this machine, and like if it's at 1, it can go to 2 or 5 or 4, and there's some probabilities down here. So you can make a 9 by 9 transition matrix here, and analyze that. And I think I had, oh no, I didn't have another clip, but a more recent application of Markov chains is this little company called Google, who got their start by being a search engine. And they have something called PageRank that sort of predicts what page you would like to see when you type in a particular search term. And the guys that came up with that, they were grad students at Stanford, and they were studying Markov chains. And they came up with some hefty duty, like I think they set a Guinness World Record as the world's largest Markov chain. But some hefty-duty Markov chains to predict what you would like to see, and they beat out all the other search engines and became synonymous with searching the internet, of course. The exact details of how their mathematics work, closely guarded secret, but the basics of it being Markov chain are pretty well understood. Okay, so let's talk about finding that steady state vector. The basic idea is if you have a stochastic matrix, let's call it S for lack of creativity, and you multiply some vector by it, you want to get that very same vector coming out. That's essentially what we're looking for. And I'm going to maybe drop the vector and matrix brackets to just say, now that we understand what we're talking about, we are trying to solve this equation. And let's do a little matrix algebra. Let's say Sx minus x equals 0. Of course, this will be a 0 vector over here, not the number 0. I can factor the x out of this. If you were factoring x's and the constants here, the coefficients were numbers, you would leave a 1 in there. But since we're talking about matrices, it's an identity matrix, the matrix version of a 1. So we are looking to solve a homogeneous matrix equation, 1 equal to 0. And the x's, again, are the unknowns. That's what we're trying to solve for. That's our steady state vector that we don't theoretically know yet. But notice what we're trying to solve is the stochastic matrix minus I equals 0. So let's go back to our sunny, cloudy, rainy matrix and see if we can set this up. Okay, there was our sunny, cloudy, rainy stochastic matrix. So there's S minus an identity matrix, 3 by 3 in this case. All that times our unknown steady state vector. And we know what it is in this case because we ran through the calculator a bunch of times, but in general we're trying to solve for this steady state vector, these 3 numbers that would be in here. And that would equal the 0 vector. Maybe I should emphasize there's going to be 3 numbers in here. Okay. So let's simplify the stuff inside the parentheses first. This is a 3 by 3 minus a 3 by 3, which can be simplified. And keep in mind when you subtract, you're just subtracting matching entries. So this will be 0.2 minus 1, so negative 0.8, 0.1, 0.05, 0.4, negative 0.3. So basically we're just subtracting 1 off the main diagonal here. 0.5, 0.4, 0.2, negative 0.55 times the unknown steady state vector equals 0, 0, 0. This is what we're trying to solve. And again, I could find the inverse. It's probably going to be a lot easier just to row reduce. I mean, either way works really. Whatever you feel like typing in your calculator to solve this. I'll go ahead and do it with row reduction. So there's what we're reducing. I'm doing the augmented matrix version. The 3 by 4 with the zeros on the ends. And it reduces down to that. So let's see what that can tell us. So there's the reduced version. Keep in mind we are trying to solve for x1, x2, and x3. So let's write it out. x1 and be minus this times x3 equals 0, but I'll solve for x1. So 0.325 x3, x2 equals 2.1 x3, and x3 equals x3. That tells us the steady state solution vector is any multiple of 0.375, 2.1, 1. And you'll probably notice those aren't the same numbers that we got before when we were running it through the calculator over and over again, because there we were using a probability vector where each of the terms was between 0 and 1 and gave a percentage, and the whole thing added up to 1. Not a problem, though. We have any multiple of this vector is a steady state vector, so we just need to scale it until the whole thing adds up to 1. So right now the whole thing adds up to 3.1, 3.475. So I just need to divide each of my entries here by 3.475. Or I'm choosing x3 to be 1 over 3.475 if you want to be formal. But basically I'm scaling the vector so it's a probability vector, so its entries add up to 1 instead of adding up to 3.475. So let's just crunch some numbers here. 0.375 divided by 3.475 is, ta-da, about 10%, 0.1079. And 2.1 divided by 3.475 is about 60.6043. And 1 divided by 3.475 is about 0.2878. So there's our true steady state vector, which essentially matches what we had before. Couple decimal places different right at the very end there. So just to recap in general, to find a steady state vector, find the steady state vector. Solve the homogeneous system of the stochastic matrix minus the identity, augmented with 0, or if you prefer the inverse version of solving here, use the inverse bit. Either way works. So this again tells us the long-term behavior of the weather, or on Chuck's pinball machine, it would tell you the probabilities of the ball being in any particular location at any particular time, or all the way back to Markov's application. What's the probability that this word will be followed by that word? And on the Google application, what's the probability that this is the page that you're looking for when you type that into Google? Okay, I think you should be ready to tackle the homework. So good luck. And congratulations on being done with Chapter 4. You rock.